clear all of this. Okay, so yeah, let's start off with this here. The first thing that we need to remember whenever we talk about trigonometry, trigonometry is only used in right angle triangles, right? And why that is so important now, because we can start linking it back to theorem of Pythagoras and then trigonometry itself. Some of the core concepts that we need to remember is lines and angles, the right angle triangle, and the Cartesian plane. So the way or the way you will use trigonometry is in these three instances. Or when you have these three things, there's certain things that we need to remember under them. A positive angle, so if you have a Cartesian plane here and you have a line, a terminal ray, a positive angle is an angle that is measured counterclockwise. A negative angle is an angle measured clockwise. So this will be a negative angle. This will be a positive angle. But we start off from the x-axis, right? So the positive x-axis. So the way the angle is born, when we talk about trigonometry, it's born like this here. You have a ray, right? A ray is one fixed point and another point that extends indefinitely. You have a ray that aligns in the positive x axis direction, and then you have another ray that overlaps with it. But then what happens is we rotate that ray about that point. And so when we rotate it, we get the terminal ray. So this is the terminal ray, right? So you got the initial ray and you have the terminal ray. And then obviously we measure the angles. If it's above, so if you're going in the counterclockwise direction, it's positive. Clockwise direction, it's negative. Right, that's that. Then we talk about something called coterminal angles. With coterminal angles, this is what happens. If you have a ray here, like this here, there's a ray, a terminal ray here, right? And this is the angle that makes it the positive angle. If I take 360 and I subtract 360 from this, right? So remember the line is here. From here, I'm taking out 360. So I'm erasing all of this and I'm going around this way. See what happens. What happens? All of this here will come out. It'll come out from that black part. And so what we left with is only this part here. So what we're saying is that this black part and this pink part gets me back to the same terminal ray, right? Just by adding or subtracting 360. So adding or subtracting 360 does not change the angle. It will lead you to the exact same terminal ray. Now, why is that significant? It's because if you have a too big angle, like an angle like 720 degrees or 755 degrees, it's too big. We can keep subtracting 360 degrees until we yield an angle that is acute. Because it's easier to work with acute angles than to work with an angle that we can't even understand. We can't even fathom what this angle is. Or we can, if an angle is too small, so negative 755 degrees, we can keep adding 360 until we have an angle that is acute, right? So that's why coterminal angles are important, because remember, you can have an angle here, you can take out 360 from it, subtract 360 from it, and you will be left with this negative angle, this negative pink angle. It gets you to the same terminal ray. It's starting from the initial ray, it's getting you to the terminal ray. This angle here starts from the initial ray and gets you to the terminal ray. So what we're saying is the lesson from this is, if I subtract 360 from it, it does not change where the terminal ray is. It gets you back to that same terminal ray. Right, so that's very important there. Then we talk about right angle triangles. Under right angle triangles, we have trigonometric ratios that we need to remember, right? And the way we remember it is SOHCAHTOA. Okay. The only limitation with this here is we can only use SOHCAHTOA when we're working with right angle triangles for acute angles. So angles that are between 0 degrees and 90 degrees. So that's the limitation. So if I want to measure an angle that is bigger than 90, like 135, I can't using the right angle triangle itself. And then if you think about it, if this is a right angle triangle and this is 90, that means that this plus this here must equal to 90 if you use some angles in a triangle. And so if at the extreme, theta will be 89 degrees and beta will be 1 degree. Okay, so 89 plus 1 gives you 90. Remember, beta can't be 0. It cannot be 0 because then you don't have a triangle. So within the bounds of the definition of a triangle, you can see this is an acute angle and that's an acute angle. So that's why we're saying when you use these ratios, just for any right angle triangle, it can only be used for values that are less than 90. So that's our limitation, right? Then if you go sine of theta is equal to opposite of hypotenuse, in the eyes of this angle, what's the side that's opposite? That side's opposite, that's the hypotenuse. Cos of theta is equal to adjacent over hypotenuse. In the eyes of this angle, what's adjacent? That's adjacent. What's the hypotenuse? That's the hypotenuse. And then tan of theta, in the eyes of this angle, what's opposite? This is opposite, that's adjacent. So it'll be opposite over adjacent. Right, that's how we can remember the trigonometric ratios there. Then we have inverse ratios, right? Inverse ratios. So basically, if you have sine of theta, the reciprocal of sine of theta is 1 over sine of theta, which is equal to, what did we say? Cosec theta. The reciprocal for cos of theta is 1 over cos of theta, which is equal to sec of theta, right? And the reciprocal for tan of theta is equal to 1 over tan of theta, which is equal to cot of theta. Now remember, reciprocal means you swap the numerator and you swap the denominator. That is very different from an inverse. Note the distinction there. And then how you remember this here, you look at the third letter, S, S, C, C, T, T, right? So that's what we call reciprocals. When we talk about an inverse, the inverse of sine is like this here, sine to the negative 1 theta, cos to the negative 1 theta, and tan to the negative 1. Where do we use this? We use this when we are solving for the angle, right? We use this when we are solving for the angle. So the reciprocals are just swapping the numerator and the denominator. The inverse, think about it like the additive inverse, multiplicative inverse. When you're solving, if you're trying to make theta the subject of the formula, right? If you have sine theta is equal to half, if you're trying to make theta the subject of the formula, no, if you have to think of it, it's like dividing by sine on both sides. But now we say take the inverse of sine on both sides. So it'll be sine to the negative 1 of half, right? Or the inverse sine, or arc sine of half will give you the angle. It'll spit out the angle there. Okay, so now remember we're still under the limitations of having the angle be acute. What happens if you want the angle to be bigger than 90? So angles like 135, 155, 100, or 275. Then we make use of the Cartesian plane. Okay, so we make use of the Cartesian plane. Now, with the Cartesian plane, there comes some things that we need to remember there. With the Cartesian plane, we have direction and we have magnitude. So what does this mean now? If I have a point that lies here, there's a point here, right? And if I measure this here to be 2 and 1, we can't just say 2 and 1, because 2 and 1 means this is 2 units and that is 1 unit, which it is, but we have to say plus 2 and plus 1, because this means that this point here lies plus 1 units away from the x-axis, and this lies plus 2 units away from the y-axis. So the plus tells you the direction. This is going up, this is going to the right. And the 2 tells you by how much. And so why this is so important is because when you output answers from it, you have to give both the magnitude and the direction. This is why that plus and that minus sign is so significant, right? So yeah. So if we're using the Cartesian plane to solve for an angle, then we need to do the following. So there's a Cartesian plane here. I want to solve for an angle that is not equal to 90 or less than 90. I want to solve for an angle that is bigger than 90. This is theta. The way you would do that is by solving what we call the reference angle, right? So to find an angle that is bigger than 90, we have to first find the reference angle. And the reference angle is the smallest angle that's from the x-axis to the terminal ray.